If the force of gravity were just slightly stronger, every star would have burned out billions of years ago, and no one would ever have existed to wonder why the dark feels so familiar at the end of a long day. This is the quiet strangeness at the heart of everything, that the universe seems, in ways both precise and improbable, arranged for the arrival of life, of consciousness, of the very awareness now settling into stillness. The numbers are almost impossibly exact. The strength of atoms, the expansion of space, the delicate balance of forces that allow carbon to form in the cores of dying stars. If any of these shifted by the smallest fraction, there would be no stars, no planets, no warmth, no breath. If these slow reflections feel like a good place to rest, subscribing means more quiet nights like this one. And so, gently, the story opens. You are lying on your back, perhaps on a blanket spread across cool grass, or maybe on a wooden deck, still holding the faint warmth of the day that has passed. And above you, the sky has opened into that familiar darkness that your ancestors knew so well. That same darkness that has greeted every generation of humans who ever tilted their faces upward and simply looked. The stars are emerging now, one by one at first, the brighter ones appearing as the last traces of twilight fade from the western horizon, and then gradually more and more of them becoming visible as your eyes adjust, as the pupils of your eyes widen to gather what light they can, until the sky above you is scattered with thousands of tiny points of light, each one impossibly distant, each one a sun in its own right, burning steadily in the cold vacuum of space. From a truly dark location, far from the electric glow of cities and towns, you might be able to see somewhere between 2,000 and 4,000 stars with your unaided eyes, depending on how clear the atmosphere is tonight, depending on how fully your eyes have adapted to the darkness, depending on the season and which portion of the sky happens to be overhead. This is not a particularly large number when you consider that our galaxy alone contains somewhere between 100 billion and 400 billion stars. But it is enough, more than enough really, to create that sense of quiet vastness that settles over you when you lie beneath an open sky. The ancient peoples who watched this same view, who tracked these same patterns of light across the dome of night, did not know the true distances involved, did not know that the light reaching their eyes had traveled for years or decades or centuries to arrive at that moment. But they felt something of what you are feeling now, that gentle awareness of being a small and temporary presence beneath something very old and very large. There is a way of thinking about cosmic time that was made famous by the astronomer Carl Sagan in his 1977 television series Cosmos, a way of compressing the entire history of the universe into a single calendar year, so that our minds, which evolved to understand seasons and days and the rhythms of ordinary life, might grasp something of the immensity of what has occurred. In this cosmic calendar, the universe begins at the first moment of January, the first, with that initial expansion of space and time and energy that we call the Big Bang, occurring at midnight as the new year begins. The first stars form sometime in January. The earliest galaxies coalesce in the weeks that follow, and our own Milky Way galaxy takes shape perhaps around March. But you would have to wait a very long time, in this compressed telling, for anything like a planet Earth to appear. Our solar system forms on the 1st of September, roughly, with the sun igniting and the planets gradually assembling themselves from the disk of dust and gas that surrounded our young star. Life appears on Earth sometime in late September. Simple single-celled organisms that would dominate the planet for billions of years. The first complex multicellular life does not emerge until December, and the dinosaurs arrive only around December the 25th, enjoying their reign for what amounts to a few days before disappearing on December the 30th. And humans, that is to say creatures recognizably like you and me, appear only in the final minutes of December the 31st. With all of recorded human history, every civilization, every empire, every book ever written, and every song ever sung, occurring in roughly the last 14 seconds before midnight. This is where you find yourself, then, lying on your blanket under these ordinary stars, in the final heartbeat of the cosmic year. The light that is entering your eyes right now left some of those stars when the dinosaurs still walked the earth, left other stars when humans were first learning to shape stone tools, left still others within living memory, though you would never know it. All of it arriving simultaneously, all of it mixing together on your retina to form this single quiet image of a star-scattered sky. You are a very recent development in a very old story. And yet here you are, with eyes that can see and a mind that can wonder, lying peacefully under the same stars that have watched over this planet through all its long history. The ancient Greek philosophers, more than 2,000 years before you were born, lay under this same sky and asked some of the same questions that might be forming, softly and without urgency, in your own mind tonight. Among them was a thinker named Democritus, who lived around 400 years before the Common Era in a Greek city called Abdera, and who proposed an idea that would eventually prove to be remarkably close to the truth. Democritus suggested that everything in the world, everything you can see and touch and taste, is made of tiny, indivisible particles, which he called atomos, meaning that which cannot be cut. He could not prove this idea, had no microscopes or particle accelerators or any of the tools that would eventually reveal the atomic structure of matter, but he reasoned his way toward it through careful thought. And in doing so, he became one of the first people to wonder seriously about why the world behaves in predictable ways, why matter follows consistent rules rather than changing its nature arbitrarily from moment to moment. This question of predictability, of why the universe seems to operate according to stable principles that the human mind can discover and describe, would occupy thinkers for millennia to come. When an apple fell from a tree in an English garden sometime in the late 17th century, or so the story goes, a man named Isaac Newton began to formulate a mathematical description of why objects fall, and in doing so, he uncovered something remarkable, something that would change humanity's understanding of its place in the cosmos. Newton published his findings in 1687 in a work called the Principia Mathematica, and what he demonstrated was that the same mathematical laws that describe an apple falling to the ground also describe the moon orbiting the Earth, also describe the Earth orbiting the Sun, also describe the motions of the planets and the comets and everything else that moves through the heavens. There was no separate physics for the sky and the ground, no divine realm operating by different rules than the earthly realm. The universe, it turned out, was unified by mathematics, governed everywhere and at all times by the same elegant principles, and these principles were of a nature that human beings, using nothing more than careful observation and patient reasoning, could actually discover. This was a profound realization, and it led to a kind of question that scientists and philosophers have been pondering ever since, a question that you might find gently forming in your own thoughts as you lie here under the stars, not demanding an answer, not urgent in any way, but present nonetheless like a soft background hum. The question is simply this: why does the universe follow rules at all? There is no obvious reason why reality should be orderly, no obvious reason why the behavior of matter and energy should be describable by mathematical equations, no obvious reason why the patterns we observe today should be the same patterns that will hold tomorrow. The physicist Albert Einstein, who did as much as anyone to uncover the deep mathematical structure of space-time and gravity, once described this as the eternal mystery of the world, by which he meant not any specific scientific puzzle waiting to be solved, but rather the astonishing fact that the universe is comprehensible at all, that it presents itself to our inquiring minds in a form that we can actually understand. You might think, lying here in the darkness, that comprehensibility is simply the natural state of things, that of course the universe should make sense, because here it is, making sense. But this is the kind of assumption that tends to dissolve when you examine it closely. The universe did not have to be this way. There is no logical requirement that the laws of physics be simple enough for creatures like us to grasp them. No guarantee that the mathematics taught in universities should happen to correspond to the actual behavior of quarks and galaxies and everything in between. Einstein found this deeply mysterious, this strange alignment between the structure of the human mind and the structure of reality. And he was not alone in his wonder. Many physicists before and since have paused in their calculations to marvel at the unreasonable effectiveness of mathematics, at the way that equations scribbled on a blackboard turn out to describe phenomena in distant galaxies with astonishing precision. And there is another layer to this quiet mystery, one that you might sense without quite being able to articulate it. It is not only that the universe follows rules, not only that these rules are mathematically describable, but also that these particular rules, with their particular constants and strengths and relationships, happen to permit the existence of someone who can lie here wondering about them. The laws of physics did not have to allow for stable atoms, did not have to allow for the formation of stars that burn steadily for billions of years, did not have to allow for the chemistry of carbon and water, and the long, slow process by which simple molecules became complex ones, and complex ones became capable of reproducing themselves, and eventually, after billions of years, became capable of looking up at the night sky and feeling wonder. And yet here you are, doing exactly that, a collection of atoms that has somehow learned to contemplate itself and its origins, lying on a small planet orbiting an ordinary star in the outer reaches of an ordinary galaxy, looking up at the light of other suns. The stars above you continue their slow wheeling, though you cannot perceive their motion in any single moment, only noticing after an hour or so that the patterns have shifted slightly, that a constellation that was in the east has risen higher, that another in the west has begun to sink toward the horizon. This motion is not the motion of the stars themselves, of course, but the motion of the Earth rotating on its axis, carrying you and your blanket and your patch of ground through space at roughly 1,000 miles per hour. Though you feel nothing of this speed, feel only stillness and quiet, and the gentle weight of your body pressing into the ground beneath you. The Earth is simultaneously orbiting the Sun at some 67,000 miles per hour, and the Sun is orbiting the center of the galaxy at nearly 500,000 miles per hour. And the galaxy itself is drifting through space at speeds that are difficult to comprehend. And yet, from your perspective, lying here in the darkness, everything is perfectly calm, perfectly still. The stars fixed in their ancient patterns, the night air cool against your skin. This calmness is itself a consequence of the laws of physics, of the way that motion is relative and acceleration is what you feel, of principles that Newton began to articulate and Einstein refined 3 centuries later. You are in motion, extraordinary motion by any everyday standard, and yet you experience peace. The universe has arranged itself in such a way that creatures on the surface of a spinning, orbiting planet can lie still and feel the quiet presence of the stars without being flung into space, without being crushed by forces they cannot see. Gravity holds you gently to the ground, neither too strongly nor too weakly. and the atmosphere above you scatters enough starlight to make the brighter stars visible, while allowing most of it to pass through. And your eyes have evolved over millions of years to be sensitive to exactly the wavelengths of light that your sun produces most abundantly. And so you see what you see, a sky full of stars, an ordinary night, and you wonder, gently and without urgency, at the deep strangeness of it all. And so we come now to consider something rather fundamental, which is to say, we turn our attention to the ingredients themselves, the raw numbers and values that seem to underpin everything we observe in the physical universe around us. You might think of this, if it helps you to picture it, as something like a recipe, though not a recipe for a cake or a loaf of bread, but rather a recipe for reality itself, for the way that matter behaves and light travels and gravity pulls and atoms hold together in the particular fashion that they do. In any recipe, of course, there are quantities, and these quantities matter a great deal. If you were baking something, you would know that the amount of flour relative to the amount of water relative to the amount of yeast makes all the difference between a successful loaf and something rather disappointing. And in much the same way, though on a vastly more fundamental level, the universe appears to have its own set of quantities, its own measurements and proportions, which physicists refer to as the fundamental constants of nature. These are numbers, simply put, that appear throughout our equations and our theories. Numbers that we have measured with extraordinary precision over the centuries, and yet numbers that we cannot, even now, derive from any deeper principle or explain from any more basic theory. They are, in a sense, simply given to us. They are what they are. And the question of why they have the particular values that they do, rather than some other values, is one of the most gently puzzling questions in all of physics. Let us begin, then, with one of the most familiar of these constants, which is the gravitational constant, usually written as a capital G. This is the number that tells us how strong gravity is, how much two masses will attract one another across a given distance. And the story of how we first measured this number is rather a lovely one, involving a man named Henry Cavendish, who conducted his famous experiment in the year 1798 in a shed on his estate in Clapham Common, which was then on the outskirts of London. Cavendish was a wealthy and rather reclusive natural philosopher, known for his extreme shyness and his meticulous experimental work. And what he did in that shed was both simple in conception and extraordinarily delicate in execution. He suspended a wooden rod from a thin wire, and at each end of this rod he attached a small lead sphere, each weighing about 0.73 kilograms. Then he brought two much larger lead spheres, each weighing about 158 kilograms, close to the smaller ones, and he watched, with infinite patience, as the gravitational attraction between the spheres caused the rod to twist ever so slightly on its wire. By measuring this tiny rotation, and by knowing the properties of the wire and the masses involved, Cavendish was able to calculate the strength of the gravitational force, and from this, to determine the value of G. The number he arrived at, translated into modern units, is approximately 6.674 times 10 to the power of -11, expressed in units of cubic meters per kilogram per second squared. It is a very small number, which reflects the fact that gravity, despite being the force we notice most in our daily lives, is actually remarkably weak compared to the other fundamental forces. What is remarkable about Cavendish's measurement is not only its accuracy, which was quite good for the time, but the fact that we still cannot explain, from any deeper theory, why G has this particular value. It is simply one of the ingredients in our recipe, measured but not derived, observed but not understood. Another constant, perhaps even more famous, is the speed of light, usually written as a lowercase c. This is the speed at which light travels through a vacuum, and it is exactly 299,792,458 meters per second, a number that is now defined rather than measured, since we have chosen to define the meter itself in terms of how far light travels in a certain fraction of a second. But it was not always so precisely known, and the first person to make an accurate measurement of the speed of light was a Danish astronomer named Ole Rømer, who did so in the year 1676, which is really quite a long time ago when you think about it. Rømer was working at the Paris Observatory, studying the moons of Jupiter, and in particular, the innermost large moon, which is called Io. Now, Io orbits Jupiter quite rapidly, completing a circuit in about 42.5 hours, and as it does so, it regularly passes behind Jupiter and disappears from view, an event called an eclipse. What Rømer noticed, over months and years of careful observation, was that the timing of these eclipses varied depending on where Earth was in its own orbit around the Sun. When Earth was closer to Jupiter, the eclipses seemed to happen a little earlier than expected, and when Earth was farther from Jupiter, they seemed to happen a little later. Rømer realized that this discrepancy could be explained if light took time to travel across the varying distance between Earth and Jupiter, and from his observations, he calculated that light must travel at about 220,000 kilometers per second. This was somewhat lower than the true value, but it was a remarkable achievement nonetheless, and it established for the first time that light travels at a finite speed, rather than instantaneously, as many had assumed. The speed of light, like the gravitational constant, is simply given to us, a number we can measure but cannot explain from any more fundamental principle. Let us turn now to a constant that is perhaps less familiar to most people, but which is deeply important in physics, and that is the fine structure constant, usually written as the Greek letter alpha. Its value is approximately 1 divided by 137, or more precisely, about 0.00729735.25693. This number governs the strength of the electromagnetic force, which is the force responsible for holding electrons in their orbits around atomic nuclei, for the behavior of light and radio waves and all forms of electromagnetic radiation, and for most of the phenomena we encounter in chemistry and everyday life. The fine structure constant was first calculated by a German physicist named Arnold Sommerfeld in 1916, while he was working on extending and refining the early quantum model of the atom that had been proposed by Niels Bohr. Sommerfeld was trying to explain certain fine details in the spectrum of hydrogen, subtle splittings of the spectral lines that Bohr's simpler model could not account for, and in doing so, he introduced this constant, which measures the strength of the electromagnetic interaction between charged particles. What is peculiar about the fine structure constant is that it is a dimensionless number, which means it has no units attached to it. It is simply a pure number, a ratio. This makes it feel even more mysterious than constants like G or C, because there are no arbitrary choices of units involved. It is just 1/137, or thereabouts, everywhere in the universe, for everyone who measures it, regardless of what system of measurement they use. And no one knows why it is 1/137, rather than 1/100, or 1/200, or some other value. The great physicist Richard Feynman once remarked that this number had been a mystery ever since it was discovered, and that all good theoretical physicists put this number up on their wall and worry about it. There is also Planck's constant, which is written as a lowercase h, and which was first introduced by the German physicist Max Planck in the year 1900. Planck was working in Berlin at the time, trying to solve a problem that had been troubling physicists for some years, which concerned the way that hot objects emit radiation. When you heat a piece of metal, for example, it first glows red, then orange, then yellow, and eventually white as it gets hotter, and the precise spectrum of light it emits, the distribution of energy across different wavelengths, follows a characteristic pattern. The classical theories of the time could not explain this pattern correctly. They predicted that hot objects should emit infinite amounts of energy at short wavelengths, which was obviously wrong and became known as the ultraviolet catastrophe. Planck found that he could solve the problem by assuming that energy was not emitted continuously, but rather in discrete packets, which he called quanta, and the size of these packets was proportional to the frequency of the radiation, with the constant of proportionality being h. The value of Planck's constant is approximately 6.626 times 10 to the power of negative 34 joule-seconds, which is an extremely small number, reflecting the fact that quantum effects are typically only noticeable at very small scales, at the level of atoms and subatomic particles. Planck's constant sets the scale of quantum mechanics. It tells us how grainy or chunky the universe is at its smallest levels, and once again, we can measure it with great precision, but we cannot explain why it has this particular value. These are just a few examples, the most famous ones perhaps, but there are many more. When physicists count up all the fundamental constants that appear in the standard model of particle physics, which is our best current theory of the elementary particles and their interactions, they find that there are approximately 25 to 30 of them, depending on exactly how you count and what you include. There are the masses of the various quarks and leptons. There is the strength of the strong nuclear force. There are parameters that describe how particles mix and transform into one another, and so on. Each of these numbers has been measured, often with remarkable precision, through painstaking experiments in laboratories around the world. But none of them can be derived from any deeper theory. They are, as the British physicist and cosmologist John Barrow once observed, numbers that appear to be put in by hand. They are inputs to our theories, not outputs. They are the settings on the dials of the universe, and someone, or something, or perhaps nothing at all, seems to have chosen those settings, and we do not know why. This sense of arbitrariness, of fine-tuned precision without explanation, has puzzled many physicists over the years. One of the earliest to comment on it in a systematic way was the great English physicist Paul Dirac, who in 1937 became fascinated by certain large number coincidences that he noticed between quantities at the atomic scale and quantities at the cosmological scale. Dirac observed, for example, that if you take the ratio of the electromagnetic force between a proton and an electron to the gravitational force between them, you get a number that is approximately 10 to the power of 40. And if you take the ratio of the size of the observable universe to the size of a proton, you get another number that is also approximately 10 to the power of 40. And if you take the ratio of the mass of the observable universe to the mass of a proton, you get a number that is approximately 10 to the power of 80, which is just 10 to the 40 squared. These coincidences struck Dirac as too remarkable to be mere chance, and he speculated that perhaps they reflected some deep connection between the physics of the very small and the physics of the very large. Perhaps even that some of the constants of nature might be changing over time as the universe expanded. This particular idea has not held up to experimental testing. The constants do appear to be truly constant, or at least to change so slowly as to be effectively constant over the age of the universe. But the sense of wonder that Dirac expressed, the feeling that these numbers are trying to tell us something, has not gone away. And so we find ourselves in a curious position. We have a recipe for the universe, a list of ingredients and quantities that we have measured with extraordinary care. We know the strength of gravity and the speed of light and the fine structure constant and Planck's constant and dozens of other numbers. We can write them down in our notebooks and program them into our computers and use them to make predictions about how the world behaves, predictions that turn out to be astonishingly accurate. But we do not know where these numbers come from. We cannot derive them from first principles. We cannot explain why they have the values they do, rather than some other values. They are simply given, simply there, like the ingredients laid out on a kitchen counter before you begin to cook, measured and weighed and ready to use, but with no note attached explaining who put them there or why they were chosen. And it is this mystery, this gentle and persistent puzzle, that lies at the heart of what physicists mean when they speak of fine-tuning, the sense that the recipe has been written with great precision, but the author remains unknown. And so we come now to consider what some have called the knife's edge, which is really just a way of saying that certain numbers in physics appear to be balanced with extraordinary precision, and that if these numbers were even slightly different, the universe would be a rather empty and lifeless place, without stars or planets or carbon atoms or anything at all, like you or me. And this observation, while it may sound dramatic when stated plainly, is simply what the mathematics tells us when we work through the equations carefully. And so we shall do that now, beginning with gravity, the most familiar of all the forces, the one that keeps your blanket resting gently upon you and holds the moon in its quiet orbit around the Earth. Gravity, you see, is actually quite weak when compared to the other fundamental forces, which may seem surprising given how obvious its effects are in daily life. But consider that a small kitchen magnet can lift a paperclip off a table, overcoming the gravitational pull of the entire Earth. And this weakness of gravity turns out to be rather important, because the strength of gravity determines how stars form and how long they burn. And the astrophysicist Martin Rees, who served for many years as the Astronomer Royal of Britain, performed calculations showing that if gravity was stronger by just 1 part in 10 to the power of 40, which is a number so large that writing it out would require a 1 followed by 40 zeros, then stars would be squeezed together so tightly that they would burn through their nuclear fuel in perhaps 1,000,000 years rather than billions. And 1,000,000 years, while a very long time for a summer holiday, is not nearly long enough for planets to cool, for oceans to form, for the slow and patient chemistry of life to unfold. And so we would have a universe of brief and violent stellar flares rather than the steady warm glow of suns, like our own, that burn reliably for billions upon billions of years. Now this particular number, 1 part in 10 to the 40th power, is worth pausing to consider, not because we need to understand it precisely, but simply to appreciate how fine a balance we are discussing. Because if you were to write out the number 1 billion, that would be a 1 followed by 9 zeros, and a trillion would be a 1 followed by 12 zeros. And these are already numbers beyond ordinary human experience. But 10 to the 40th power is a number so vast that it exceeds the number of atoms in a human body, exceeds the number of grains of sand on all the beaches of Earth, exceeds even the number of atoms in the sun. And yet the strength of gravity appears to be set within this tolerance, as if someone had adjusted a dial with almost unimaginable care. Though of course we are not suggesting anyone did any such thing. We are simply noting what the physics reveals when examined closely. And gravity is only the beginning of this story, because there are other forces in nature, forces that operate inside the atomic nucleus, and these forces have their own curious balances. And perhaps the most remarkable of these involves the way that carbon is made inside stars. Which brings us to a scientist named Fred Hoyle, an Englishman from Yorkshire who was known for his rather colourful opinions and his willingness to follow an argument wherever it led, even when it led somewhere uncomfortable. And in 1953, Hoyle was thinking about a problem that had puzzled physicists for some time, which was simply this: how does the universe make carbon? Carbon, you see, is not the simplest of elements. It is not hydrogen with its single proton or helium with its two, but rather a more complex arrangement of 6 protons and 6 neutrons and 6 electrons. And the question of how the universe creates carbon turns out to be surprisingly difficult to answer, because you cannot simply smash 2 lighter atoms together and get carbon directly. The mathematics does not work out, and so physicists had to consider a more elaborate process, one that takes place in the cores of red giant stars, where temperatures reach hundreds of millions of degrees, and helium nuclei move very quickly indeed. This process is called the triple alpha process, and the name comes from the fact that a helium nucleus is sometimes called an alpha particle for historical reasons relating to early studies of radioactivity. And the process works like this. First, 2 helium nuclei collide and briefly fuse together to form an isotope of beryllium, specifically beryllium-8. But this beryllium is deeply unstable and exists for only about 10 to the minus 16 seconds before falling apart again, which is to say, it exists for less than a trillionth of a second. And during that impossibly brief moment, a third helium nucleus must arrive and collide with the beryllium. And if this happens, the result is a carbon-12 nucleus. And this is how carbon is made, through this delicate dance of 3 particles meeting in just the right way, at just the right moment. But here is where Hoyle noticed something peculiar, because when he calculated the probability of this triple collision happening, using the known properties of the particles involved, the numbers came out far too small. The universe should not contain very much carbon at all, and yet here we are, made largely of carbon, living on a planet with carbon-based oceans and carbon-based atmosphere and carbon-based life everywhere we look. And this discrepancy between prediction and observation troubled Hoyle. And so he reasoned backwards from the existence of carbon to what must be true about nuclear physics. Specifically, Hoyle predicted that the carbon-12 nucleus must have a special property called a resonance at a very particular energy level, 7.65 million electron volts above its ground state. Because if such a resonance existed, it would greatly increase the probability of the triple alpha process succeeding, making carbon production efficient enough to explain what we observe. And this was a bold prediction, because Hoyle was not primarily a nuclear physicist. He was an astrophysicist and cosmologist. And he was telling the nuclear physicists that their picture of the carbon nucleus must be incomplete, that there must be an energy level they had not yet discovered, sitting precisely where he said it would be. And so a group of experimentalists at the California Institute of Technology, led by William Fowler, set out to test Hoyle's prediction. And they bombarded nitrogen atoms with protons and carefully measured the gamma rays that emerged, looking for evidence of this hypothetical resonance. And they found it, not approximately where Hoyle had said, but precisely there, at 7.65 million electron volts. And this discovery helped to explain how the universe manufactures the carbon that makes up so much of living things. And William Fowler would later receive the Nobel Prize in Physics in 1983 for his work on nuclear reactions in stars, work that grew directly from Hoyle's remarkable theoretical prediction. And while it is often noted that Hoyle himself did not share in that Nobel Prize for reasons that remain a matter of some historical discussion, His insight was nonetheless recognized as one of the great achievements of 20th century astrophysics. Now Hoyle, reflecting on this discovery later in his life, made a comment that has been quoted many times since. He said that the universe looks like a put-up job, which is an informal English expression meaning something arranged or contrived, like a stage set rather than a natural occurrence. And Hoyle was not a religious man by any conventional measure. He did not believe in traditional notions of creation. And so this comment was not meant to endorse any particular theological view, but rather to express his genuine puzzlement at how precisely the constants of physics seem to be adjusted to permit complexity, to permit stars that burn long enough, to permit carbon that forms efficiently enough, to permit eventually creatures like ourselves who can wonder about such things. And there is yet another force we must consider, the strong nuclear force, which is the force that holds protons and neutrons together inside the atomic nucleus, overcoming the electrical repulsion between protons, which would otherwise push them apart. And this force, too, appears to be balanced with great precision, because calculations suggest that if the strong force were about 2% stronger than it is, then in the early universe, protons would have fused together so efficiently that almost all hydrogen would have been consumed, converted into helium and heavier elements. And since hydrogen is the fuel that stars burn in their main sequence phase, the long, stable phase that our Sun is currently in, a universe without hydrogen would be a universe without long-lived stars, without the patient billions of years needed for planets to develop conditions suitable for life. And conversely, if the strong force were about 2% weaker than it is, then protons and neutrons would not stick together well enough to form nuclei at all, and the universe would contain only hydrogen, just single protons with their electrons, no helium, no carbon, no oxygen, no iron, nothing but hydrogen forever, which would make for a very simple and rather boring cosmos, with no possibility of complex chemistry, no possibility of molecules or crystals, or the intricate machinery of life. And so the strong force appears to be set within a range of perhaps 4% total, neither too strong nor too weak, just enough to permit the full periodic table of elements that we find around us. The physicist Freeman Dyson, who made important contributions to quantum electrodynamics and many other fields, reflected on these observations in 1971, and he wrote that the universe in some sense seems to have known that we were coming, which is a poetic way of expressing the same puzzlement that Hoyle felt, the sense that the laws of physics appear almost as if they were chosen with future observers in mind. And again, Dyson was not making a theological argument. He was a careful scientist, simply noting what the data suggested, that the constants of nature fall within narrow ranges that permit complexity, and that this seems at the very least worthy of notice. It is worth emphasizing that none of this proves anything about why the universe is arranged as it is. These observations about fine-tuning are simply observations. They tell us what is the case, but not why it is the case. And thoughtful people have proposed many different explanations, some involving multiple universes with different constants of which we inhabit, one that happens to permit observers, others involving deeper physical principles that we have not yet discovered that might explain why the constants must take the values they do, and still others involving various forms of design or purpose. And all of these remain open questions, matters for ongoing investigation and reflection. And you need not resolve them tonight. You need only rest in the knowledge that these questions exist, and that clever people are thinking about them carefully. For now, it is enough to notice that you exist, that you are made substantially of carbon atoms forged in the cores of ancient stars, through the triple alpha process, that those stars burned for billions of years, because gravity is precisely weak enough to allow it, that the strong force holds the nuclei together in your body without having consumed all the hydrogen in the early universe, and that all of these balances, all of these knife-edge precisions, have somehow come together to produce this moment, this breath, this quiet evening, this gentle awareness that wonders at its own existence without needing to explain it fully. And that is perhaps enough to carry with you as you settle more deeply into rest. And now we turn our attention outward, far beyond the atoms in your body and the forces that hold them together, outward to the universe itself, to the largest scales imaginable, where the same curious pattern of precise arrangement reveals itself once more, as though the cosmos were designed with the same meticulous care that a watchmaker might bring to the smallest gear in a delicate mechanism. Though of course we make no claims about designers or purposes, only observations, only measurements, only the gentle accumulation of facts that scientists have gathered over decades of patient work. The universe, you see, appears to be what some researchers have called a Goldilocks Cosmos, neither too hot nor too cold, neither too dense nor too sparse, neither expanding too quickly nor collapsing too soon, but rather balanced in a way that permits, among other things, the existence of galaxies and stars and planets and, eventually, living things capable of wondering why any of this should be so, which is a question that has occupied philosophers for centuries and physicists for somewhat less time, though their contributions have been no less profound. Let us begin with something called the cosmological constant, which is a term that describes the energy of empty space itself, the energy that exists even when you remove all the matter and all the radiation and all the particles from a region of the universe, leaving behind only the vacuum, which turns out not to be empty at all, but rather fizzing with quantum fluctuations, with particles and antiparticles appearing and disappearing in pairs, borrowing energy from the universe for the briefest of moments before returning it, as though the vacuum were a kind of foam, always bubbling, never quite still. When physicists attempt to calculate how much energy this quantum foam should contribute to the universe, using the well-established principles of quantum field theory, they arrive at an answer that is, to put it mildly, problematic. An answer that does not match what we observe. An answer that is larger than the observed value by a factor of approximately 10 to the power of 120, which is a number so large that it defies ordinary comprehension. A 1 followed by 120 zeros. And this discrepancy has been called by some the worst prediction in the history of physics, though others prefer gentler terminology. The physicist Steven Weinberg, who would later receive the Nobel Prize for his work on the unification of fundamental forces, considered this puzzle carefully in 1987, and he made a calculation that has since become famous, or at least as famous as such calculations can be, in which he asked what range of values for the cosmological constant would permit a universe in which galaxies could form, in which matter could clump together under gravity rather than being torn apart by the expansion of space, and he found that the observed value lies within a very narrow window, a window that represents only a tiny fraction of the theoretically possible range. And he noted, with characteristic understatement, that this was rather convenient for us, since we happen to live in galaxies, since our solar system and our planet and our bodies are made of matter that condensed from primordial clouds. And if the cosmological constant were much larger, none of this condensation would have occurred. This brings us to another puzzle, one that was identified by the physicist Alan Guth while he was working at the Massachusetts Institute of Technology in the years spanning 1979 and 1980, during a period when he was developing what would become known as inflation theory, a theory that proposes a brief but dramatic expansion of the universe in its earliest moments. And the puzzle that concerned Guth was something called the flatness problem, which has nothing to do with whether the universe is literally flat in the sense of a tabletop, but rather with the relationship between the universe's density and something called the critical density. The critical density is, in essence, the amount of matter and energy that would cause the universe to be perfectly balanced between eternal expansion and eventual collapse. Like a ball thrown upward at precisely the escape velocity of a planet, never quite falling back, but never quite escaping either, hovering in perpetual equilibrium. And what Guth and others noticed was that the universe's actual density appears to match this critical density with extraordinary precision, a precision that seems almost unreasonable when one considers how things might have been otherwise. In the earliest moments of the universe, in the first fractions of a second after the beginning, this match between actual density and critical density would have needed to be accurate to approximately 1 part in 10 to the power of 62, which is another number that challenges our intuition, a 1 followed by 62 zeros. And any deviation from this precision, any slight excess or deficit in the primordial density, would have been amplified as the universe evolved, leading either to a rapid collapse back into a singularity or to an expansion so swift that matter would have dispersed before galaxies could form, before stars could ignite, before planets could coalesce from the debris of stellar explosions, and we would not be here to wonder about any of it. The flatness problem is one of several puzzles that inflation theory attempts to address. And while we shall not delve too deeply into the mathematics of inflation, it is enough to say that this theory proposes a mechanism by which such fine-tuning might arise naturally, through the dynamics of fields and energies in the early universe. Though whether inflation truly solves the puzzle or merely relocates it to a different set of initial conditions remains a matter of ongoing discussion among cosmologists, who are, as a rule, comfortable with such discussions. There is yet another asymmetry we must consider, another imbalance that seems improbable and yet essential. And this is the asymmetry between matter and antimatter, between the particles that make up your body and the antiparticles that are their mirror images, identical in mass, but opposite in charge and certain other properties. And when a particle meets its antiparticle, both are annihilated, converted entirely into energy, into photons of light, leaving nothing behind but radiation. In the early universe, matter and antimatter were created in nearly equal amounts, as the intense energies of the first moments produced particle-antiparticle pairs in unimaginable profusion. And when the universe cooled, these pairs met and annihilated, filling the cosmos with light, with the radiation that we can still detect today as the cosmic microwave background, the faint afterglow of that primordial annihilation. And yet somehow, despite all this mutual destruction, a small residue of matter survived, a slight excess of particles over antiparticles, and this residue is everything you see around you, every galaxy, every star, every grain of sand, every cell in your body. The Soviet physicist Andrei Sakharov, who was also known for his work on nuclear physics and his later efforts in human rights advocacy, considered this puzzle in 1967, and he identified 3 conditions that would be necessary for such an asymmetry to arise, 3 requirements that any theory of matter-antimatter imbalance must satisfy, and these have become known as the Sakharov conditions. And while the details are technical, the essential point is that the laws of physics must be slightly different for matter and antimatter, must treat them in ways that are almost but not quite symmetrical, and experiments have confirmed that such slight differences do exist, though whether they are sufficient to explain the observed imbalance remains an open question. The magnitude of this asymmetry is itself remarkable, for it amounts to only about 1 extra matter particle for every billion particle-antiparticle pairs, 1 survivor among a billion annihilations. And yet this tiny excess was enough, when multiplied across the vast volume of the early universe, to provide all the matter we observe today, all the hydrogen and helium that would later fuse in stars, all the carbon and oxygen and iron that would form in stellar cores and scatter across space in supernova explosions, all the material from which planets and life would eventually emerge. The cosmic microwave background that I mentioned a moment ago has been studied with increasing precision over the decades, and one of the most significant recent contributions to our understanding came from the Planck satellite, which was launched by the European Space Agency in 2009, and which spent several years mapping the microwave sky with unprecedented accuracy, measuring the temperature of this ancient light at millions of points across the heavens. And what the Planck satellite found was that this radiation is remarkably uniform, varying from point to point by only about 1 part in 100,000, a uniformity that presents its own puzzle. For if different regions of the early universe had never been in contact with one another, if light had not had time to travel between them and allow them to exchange energy and equilibrate their temperatures, then why should they have the same temperature? Why should the cosmic microwave background be so smooth, so homogeneous, so lacking in large-scale variations? And this is another puzzle that inflation theory attempts to address, proposing that regions which seem widely separated today were once in close contact before inflation stretched them apart. The small variations that the Planck satellite did detect, the tiny fluctuations of 1 part in 100,000, are themselves significant, for they represent the seeds of all cosmic structure, the slight density enhancements that would grow over billions of years into galaxies and clusters of galaxies, the initial conditions from which everything we observe would eventually develop, and the properties of these fluctuations, their amplitude and their statistical distribution, match the predictions of inflationary models with remarkable precision, which is either a confirmation of those models or a coincidence of considerable magnitude. Behind all of these specific puzzles lies a deeper question, one that science alone may not be equipped to answer, and it is a question that philosophers have pondered for centuries, perhaps most famously articulated by the German philosopher and mathematician Gottfried Wilhelm Leibniz in 1714. When he asked why there is something rather than nothing, why the universe exists at all, why there should be matter and energy and space and time rather than simply an eternal void. A question so fundamental that it seems almost childlike in its simplicity, and yet no one has ever answered it to universal satisfaction. Science can describe how the universe behaves, can trace its history back through billions of years, to the first moments after the beginning, can identify the laws that govern its evolution and the initial conditions from which it emerged. But whether science can explain why there should be a universe at all, why there should be laws of nature, why those laws should take the particular form they do rather than some other form, these are questions that press against the boundaries of the scientific method, that may require philosophical or theological or simply humble agnostic responses. The pattern of apparent fine-tuning that we have been discussing, the cosmological constant and the flatness and the matter-antimatter asymmetry and the uniformity of the cosmic microwave background, was given a formal name in 1973 at a symposium held in Krakow, Poland, commemorating the 500th anniversary of the birth of Copernicus, when the physicist Brandon Carter introduced the term anthropic principle to describe the observation that the universe must be compatible with the existence of observers, that we should not be surprised to find ourselves in a universe with properties that permit our existence, since we could not find ourselves anywhere else. Carter distinguished between a weak version of this principle, which is essentially a selection effect, a reminder that we can only observe conditions compatible with our own existence, and a stronger version that makes more controversial claims about the universe being in some sense designed for life. And the debates about what the anthropic principle means and whether it constitutes an explanation or merely a restatement of the puzzle have continued in the decades since Carter's talk, with thoughtful people on various sides of the question. What we can say with confidence is that the universe we inhabit is, by any reasonable measure, a remarkable place, that the conditions which permit stars to shine and planets to form and chemistry to proceed and life to emerge are balanced with a precision that seems almost excessive, almost extravagant. And whether this precision indicates something deep about the nature of reality, something we have not yet understood, or whether it is simply how things happen to be, requiring no further explanation, is a question that each of us must contemplate in our own time and in our own way. For now, as you rest, as your breathing slows and your thoughts drift, it is enough to know that you exist in this particular universe, this Goldilocks Cosmos, where the constants and the conditions and the primordial asymmetries have conspired, if that is the right word, to permit everything you know and love and wonder about. And there is something peaceful in that knowledge, something restful in the recognition that you are part of something vast and precisely arranged, even if we do not fully understand why. When you look up at the night sky, you are doing something that astronomers have done for thousands of years, though the tools we use now are rather different from the ones our ancestors employed. The telescopes of the modern era have shown us things that no one could have imagined even a century ago. And these discoveries, made quietly in observatories and research stations around the world, have revealed that the universe operates according to rules so precisely balanced that even small changes would make existence as we know it impossible. This is not a matter of philosophy or speculation, but of careful measurement, of numbers recorded and verified and checked again. And the story of how we came to understand this begins with light from dying stars and the patient work of scientists who simply wanted to know how fast the universe was expanding. In the late 1990s, two teams of astronomers were engaged in what seemed like a straightforward project, which was to measure the rate at which the expansion of the universe was slowing down. Everyone expected that it would be slowing down. You see, because gravity pulls things together, and all the matter in the universe should have been acting as a kind of brake on the outward rush that began with the Big Bang. The two teams, one led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the other led by Brian Schmidt at the Australian National University, along with Adam Rees at Johns Hopkins University, were using the Hubble Space Telescope and ground-based observatories to study a particular type of stellar explosion called a type Ia supernova. These supernovae are remarkably useful to astronomers for reasons that we shall explore in a moment, and both teams were collecting data on distant examples of these explosions in order to calculate how quickly the universe's expansion had decelerated over the past several billion years. Type Ia supernovae occur in binary star systems where one of the stars is a white dwarf, which is the dense remnant of a star that has exhausted its nuclear fuel. When the white dwarf pulls enough material from its companion star to reach a critical mass, approximately 1.4 times the mass of our Sun, it undergoes a sudden thermonuclear explosion of extraordinary violence. The important thing about these explosions, from the perspective of astronomers trying to measure cosmic distances, is that they all happen at essentially the same mass threshold, which means they all release approximately the same amount of energy and therefore shine with approximately the same intrinsic brightness. This makes them what astronomers call standard candles, objects whose true luminosity is known, so that by measuring how bright they appear from Earth, one can calculate how far away they are. A candle that appears dim might be a small candle nearby or a large candle very far away. But if you know that all the candles are the same size, then the dimmer ones must simply be more distant. And this is precisely the principle that Perlmutter, Schmidt, and Rees were applying to supernovae scattered across the observable universe. What they found, when they analyzed their data, was something that no one had anticipated. The distant supernovae were dimmer than they should have been if the universe's expansion was slowing down, which meant they were farther away than expected, which meant the universe was not slowing down at all. It was speeding up. The expansion of the cosmos was accelerating, as if some invisible force were pushing everything apart faster and faster over time. Both teams arrived at this conclusion independently, using different supernovae and different analysis methods. And when they published their results in 1998, the scientific community was forced to confront an entirely new picture of the universe. For this discovery, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011, recognition of work that had fundamentally changed our understanding of cosmic evolution. The force responsible for this acceleration was given the name dark energy, not because anyone knew what it was, but precisely because no one did. It was dark in the sense of being hidden from our understanding, a form of energy that permeated all of space and acted in opposition to gravity, pushing the universe apart rather than pulling it together. The existence of dark energy meant that the equations describing the universe required a new term, a cosmological constant or something like it. And the value of this constant turned out to be extraordinarily small. So small that it had no significant effect on the universe for billions of years after the Big Bang, only becoming dominant as matter spread out and thinned, and gravity's influence weakened. If the value of dark energy had been even slightly larger, the universe would have expanded so rapidly that galaxies could never have formed. And if it had been negative rather than positive, the universe would have collapsed back on itself before stars could ignite. The fact that it has precisely the value it does, small enough to allow structure to form, but present enough to drive the current acceleration, is one of the most striking examples of fine-tuning that modern cosmology has revealed. To understand the composition of the universe more precisely, astronomers needed to study not just supernovae, but the oldest light in existence, the afterglow of the Big Bang itself. This light, called the cosmic microwave background radiation, was first detected in 1965 by Arno Penzias and Robert Wilson, who were trying to eliminate sources of noise from a radio antenna in New Jersey, and found instead a faint hiss that seemed to come from every direction in the sky. This radiation is the remnant of a time, about 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with protons to form neutral hydrogen, allowing light to travel freely for the first time. The light that was released in that moment has been traveling through space ever since, stretching to longer wavelengths as the universe expanded, until it now appears not as visible light, but as microwaves with a temperature of just 2.7 degrees above absolute zero. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, known as WMAP, on a mission to map tiny variations in the temperature of this cosmic microwave background across the entire sky. The probe was positioned at a point in space called the second Lagrange point, or L2, which lies about 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the gravitational pull of the Sun and Earth combine in such a way that a spacecraft can maintain a stable position relative to both bodies, providing an ideal vantage point for observations that need to be kept far from Earth's interfering heat and radio emissions. Over the course of 9 years, from 2001 to 2010, WMAP collected data that allowed scientists to create the most detailed map ever made of the early universe, showing patterns of slightly warmer and slightly cooler regions that correspond to variations in density that would eventually grow into the galaxies and galaxy clusters we see today. The WMAP data, combined with other observations, allowed cosmologists to determine with remarkable precision what the universe is made of. The results were humbling for anyone who thought that the ordinary matter of which we and our planet are composed might be the dominant stuff of existence. Dark energy, the mysterious force driving the acceleration of cosmic expansion, accounts for approximately 68% of the total energy content of the universe. Dark matter, another invisible substance that we have never directly detected, but whose gravitational influence we can measure, makes up about 27%. And ordinary matter, the atoms and molecules from which stars and planets and people are built, comprises only about 5% of the cosmic total. We are, it turns out, a rather minor ingredient in the recipe of the universe, swimming in a sea of substances we can neither see nor touch nor fully understand. The evidence for dark matter had been accumulating for decades before these precise measurements were made. In the 1970s, an astronomer named Vera Rubin was studying the rotation of spiral galaxies, measuring how fast stars at different distances from the galactic center were orbiting. According to the laws of gravity, stars at the outer edges of a galaxy should move more slowly than stars near the center, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. But Rubin found, again and again, that the outer stars were moving just as fast as the inner ones, which could only be explained if there were far more mass in the galaxies than could be accounted for by the visible stars. This invisible mass, distributed in a vast halo around each galaxy, came to be called dark matter, and Rubin's careful observations, made with a spectrograph designed to measure the Doppler shifts of starlight, provided some of the most compelling evidence that the universe contained large quantities of matter that did not emit or absorb light in any way we could detect. The patterns revealed by WMAP were not only in the temperature variations of the cosmic microwave background, but also in the distribution of galaxies across the sky, patterns that carried information about the physics of the early universe. In 2005, astronomers analyzing data from the Sloan Digital Sky Survey announced the detection of baryon acoustic oscillations, subtle ripples in the distribution of galaxies that corresponded to sound waves propagating through the hot plasma of the early universe. Before the release of the cosmic microwave background, the universe was so hot and dense that matter and radiation were locked together, and pressure waves could travel through this primordial soup much as sound waves travel through air. When the universe cooled enough for light to escape, these waves froze in place, leaving their imprint on both the cosmic microwave background and the distribution of matter that would later form galaxies. By measuring the characteristic scale of these oscillations, astronomers gained another independent method of probing the geometry and composition of the universe, and the results confirmed what the supernova observations and the microwave background had already suggested. The investigation of dark energy continues today with increasingly sophisticated instruments. In July of 2023, the European Space Agency launched the Euclid mission, a space telescope designed specifically to map the distribution of galaxies and dark matter across more than a third of the sky. Operating from the same Elta Lagrange point where WMAP once stood watch, Euclid is creating the largest and most accurate three-dimensional map of the universe ever attempted, looking back in time more than 10 billion years to trace how the structure of the cosmos has evolved under the competing influences of gravity and dark energy. The data from Euclid will help scientists determine whether dark energy has been constant throughout cosmic history or whether it has changed over time. A question with profound implications for our understanding of the fundamental forces of nature. All of these observations, from Rubin's galaxy rotations in the 1970s to the Hubble Space Telescope's supernova measurements in the 1990s, to WMAP's mapping of the cosmic microwave background in the 2000s, to Euclid's ongoing survey of dark matter, point toward the same remarkable conclusion. The universe is not only stranger than we imagined, filled with invisible matter and energy that we cannot directly perceive, but it is also balanced on a knife's edge of physical constants and initial conditions that permit complexity to exist. The amount of dark energy, the ratio of matter to radiation in the early universe, the tiny fluctuations in density that seeded the formation of galaxies, all of these quantities have values that fall within narrow ranges compatible with a universe where stars can form and burn steadily for billions of years, where heavy elements can be forged in stellar cores and scattered by supernovae, where planets can coalesce from clouds of gas and dust, and where, on at least one small world, living things can arise and eventually build telescopes to look back at the light from the beginning of time. The fine-tuning we speak of is not a metaphor or an interpretation, but a fact established by decades of careful measurement, recorded in the data from instruments orbiting far from Earth, and in the images of galaxies whose light has traveled for billions of years to reach us. The numbers are what they are, and they tell us that existence as we know it depends on a universe tuned to extraordinary precision, a precision we are only beginning to appreciate as our tools grow more sensitive and our maps of the cosmos grow more complete. And now we come to a possibility that extends far beyond the edges of what we can see, far beyond even the light that has had time to reach us since the beginning of our observable cosmos. And this possibility suggests that our universe, with all its seemingly improbable constants and its delicate arrangements, may be just one among an unimaginably vast collection of other universes, each with its own properties, its own physical laws perhaps, its own separate existence unfolding in ways we cannot directly observe. And this collection, this ensemble of realities, is what physicists and cosmologists sometimes call the multiverse, a word that sounds rather grand, but which we shall explore here in the most gentle and measured way, as simply one of several ideas that thoughtful people have proposed to explain why things are the way they are. The notion that there might be other worlds beyond our own is not entirely new. Of course, as philosophers and dreamers have contemplated such ideas for centuries. But what distinguishes the modern scientific versions of this concept is that they emerge, sometimes unexpectedly, from the mathematics of theories that were developed for entirely different purposes. Theories about the very early universe, theories about the fundamental structure of matter and energy, theories about the strange behavior of particles at the smallest scales. And in each case, the mathematics seems to point, almost of its own accord, toward the possibility of multiplicity, of many worlds rather than just one. Though whether this mathematical pointing constitutes genuine evidence is a question we shall touch upon in due course. One of the pathways to this idea of multiple universes comes from our understanding of what may have happened in the first tiny fraction of a second after the beginning of time, during that period of extraordinarily rapid expansion that cosmologists call inflation. And here we encounter the work of a physicist named Andrei Linde, who has spent much of his career at Stanford University thinking about these earliest moments, and who, in 1983, developed a version of inflationary theory called chaotic inflation, building upon earlier work by Alan Guth and others. And what Linde realized was that the inflationary process, once it begins, may never entirely stop. that while inflation might end in one region of space, allowing matter and energy to settle into the familiar forms we observe, in other regions, the inflation could continue, and those regions would grow at such tremendous rates that they would spawn still more inflating regions. And this process, sometimes called eternal inflation, would produce an endless foam of expanding bubbles, each bubble a universe unto itself, each potentially possessing different physical properties, depending on precisely how the inflation ended in that particular pocket of space. And we, in this picture, would find ourselves inside just one such bubble, one among countless others that are forever beyond our reach, because the space between us expands faster than light could ever cross it. The idea of eternal inflation gives us a mechanism for producing many universes, but it does not, by itself, tell us why those universes would have different properties, why the constants of nature might vary from one bubble to another. And here we turn to a different area of physics entirely, to the attempts by theorists to find a deeper framework that unifies all the forces and particles we observe. And one of the leading candidates for such a framework is string theory, which proposes that the fundamental constituents of reality are not point-like particles, but rather tiny vibrating strings of energy. And what became apparent as physicists explored the mathematical structure of string theory was that the theory does not predict a unique set of physical laws, but rather allows for an enormous number of possible configurations, an enormous number of ways that the extra dimensions required by the theory could be curled up and hidden, each configuration corresponding to a different set of apparent physical laws, a different set of particle masses and force strengths. And in 2003, a physicist named Leonard Susskind gave a name to this vast space of possibilities, calling it the landscape, the string theory landscape, and he estimated that the number of distinct possible configurations might be something like 10 to the power of 500, which is a number so large that writing it out would require more zeros than there are atoms in the observable universe. And if each of these configurations is realized somewhere, in some bubble of the eternally inflating multiverse, then suddenly the improbability of our own universe begins to look rather different. For in such a vast ensemble of possibilities, the existence of at least one universe with properties suitable for life would seem almost inevitable. There is another route to the idea of many worlds, one that comes not from cosmology, but from the foundations of quantum mechanics, that strange and beautiful theory that describes the behavior of matter and energy at the smallest scales. And in 1957, a graduate student at Princeton University named Hugh Everett, working under the supervision of the renowned physicist John Wheeler, proposed an interpretation of quantum mechanics that has come to be called the many worlds interpretation. And Everett's idea was both simple and radical, for he suggested that when a quantum system appears to make a random choice between different possible outcomes, what actually happens is that all the outcomes occur, but in separate branches of reality that split off from one another at that moment, so that every quantum event produces a proliferation of parallel worlds, each containing a different version of history. And we, as observers, find ourselves in just one branch, unaware of all the others. And while Everett's interpretation remains controversial, it is taken seriously by many physicists today because it provides a mathematically consistent way of understanding quantum mechanics without the need for the mysterious collapse of the wave function that other interpretations require. And if the many worlds interpretation is correct, then the number of parallel realities would be beyond any counting, growing with every quantum event that occurs anywhere in the cosmos. In 2003, a cosmologist named Max Tegmark, who had been thinking deeply about the mathematical structure of reality, proposed a classification scheme for the different types of multiverses that physicists had imagined, organizing them into a four-level hierarchy, with the first level being simply the regions of space beyond our cosmological horizon, regions we cannot see but which are presumably much like our own, governed by the same laws, and the second level corresponding to the bubble universes of eternal inflation, where the laws might differ, and the third level corresponding to the quantum parallel worlds of Everett's interpretation, and the fourth and most speculative level being a vast ensemble of all mathematically possible structures, all self-consistent mathematical systems, each of which, Tedmark suggested, might have some form of existence, might be real in some sense, and our universe would be just one such structure, distinguished from the others only by the fact that it is the one we inhabit. And while this classification may seem abstract, it provides a useful way of thinking about the different proposals, of understanding how they relate to one another, and what each would imply about the nature of existence. Among the more remarkable proposals for how universes might come into being is one put forward in 1982 by Alexander Vilenkin, a physicist working at Tufts University, who suggested that a universe could emerge from nothing at all, not from empty space, which is still something, but from genuine nothingness, no space, no time, no matter, no energy, through a process of quantum tunneling. The same process that allows particles to pass through barriers they classically could not surmount. And Vilenkin showed mathematically that such a tunneling event could produce a tiny seed of space-time that would then inflate into a full-fledged universe. And this idea, while strange, is taken seriously by cosmologists because it follows from the application of quantum mechanics to gravity and space-time. And it suggests that the question of why there is something rather than nothing might have a physical answer that the laws of physics themselves might permit, or even require, the spontaneous appearance of universes from the void. A different and quite imaginative proposal came from the physicist Lee Smolin in 1992, who suggested a mechanism he called cosmological natural selection. And Smolin's idea was inspired by biological evolution, by the way in which natural selection shapes living things over many generations. And he proposed that when a black hole forms, when matter collapses under its own gravity beyond a certain point, it might give birth to a new universe in some sense, a universe that would have physical laws slightly different from its parent, just as offspring in biology differ slightly from their parents. And if the new laws were such as to favor the formation of more black holes, then that universe would produce more offspring, and over countless generations of universes, the laws would tend to evolve toward configurations that maximize black hole production. And since the formation of black holes requires stars, and stars require the same physical conditions that permit complex chemistry and life, this process would naturally lead to universes like our own, not through design and not through mere chance, but through a kind of cosmic evolution, a selection process operating across the generations of worlds. Now, we should pause here and note that all of these proposals, while fascinating and mathematically intriguing, raise a question that has been the subject of serious debate among scientists and philosophers. The question of whether the multiverse is properly a scientific hypothesis at all, or whether it ventures into territory better described as metaphysics, a speculation beyond what science can test. And in 2014, two distinguished scientists named George Ellis and Joseph Silk published a commentary in the journal Nature, in which they raised precisely these concerns, arguing that theories which postulate unobservable entities, universes we can never detect, phenomena that leave no trace in our measurements, risk departing from the standards of empirical science, risk becoming untestable, and therefore, in some sense, unfalsifiable. And while proponents of multiverse ideas argue that these theories make predictions about our own universe, about statistical patterns we might observe, the debate continues. And thoughtful people disagree about whether we are on the threshold of a profound expansion of our understanding, or whether we are being tempted by elegant mathematics into realms where experiment cannot follow. What we can say is that the multiverse provides one possible response to the puzzle of fine-tuning, a response that invokes no purpose and no design, but only the vast impersonal profusion of possibilities. And in this picture, the reason we observe a universe with just the right constants for our existence is simply that we could not exist in any other kind of universe. We could not be here asking questions in a cosmos where atoms were unstable or stars could not form. And this way of thinking is called the anthropic selection effect. The observation that our very existence as observers places constraints on what we can observe, that we are necessarily in a universe compatible with our being here. Just as a fish, were it to wonder why it found itself in water rather than on dry land, might eventually realize that it could not find itself anywhere else and still be wondering. And while this reasoning is straightforward, almost tautological, it gains explanatory power if there truly are many universes with varying properties. For then our situation becomes less a matter of improbable cosmic luck and more a matter of inevitable location within an ensemble vast enough to include every possibility. And so we have explored, in this gentle way, the landscape of ideas that collectively go by the name of the multiverse. From the eternally inflating bubbles of Lind's cosmology, to the 10 to the 500 possibilities of the string theory landscape, to the branching quantum worlds of Everett's interpretation, to Vilenkin's universes tunneling from nothing, to Smolin's cosmic natural selection. And we have noted that this remains an area of active discussion, where the boundaries between physics and philosophy are not always clear. And we present these ideas not as established truth, but as one direction in which human thought has turned in its attempt to understand why the universe is the way it is, to understand why we are here at all, drifting now toward rest, toward the gentle boundary of waking and sleep, where such questions can settle like leaves on still water, requiring no immediate answer, only the quiet acknowledgement that minds have wondered, and will continue to wonder, about the nature of existence, about the possibility of other worlds, and about our place in whatever larger reality may surround the small bright bubble of the cosmos we call home. And so we come now to consider that perhaps, after all, there is no need to invoke the fact of your existence to explain why the universe takes the form it does. Perhaps the constants are not arbitrary settings that happen to permit life, but rather necessary consequences of some deeper structure we have not yet discovered. This is the hope that has animated a particular strain of theoretical physics for nearly a century, the quiet conviction that beneath the apparent contingency of nature lies an elegant inevitability, that the universe could not have been otherwise, and that we will someday understand why. This search for deeper laws represents an alternative to anthropic reasoning, a path that does not rely upon the observation that we are here to explain why things are as they are. Instead, it seeks a theory of everything, a single mathematical framework from which all the constants of nature, all the forces and particles and interactions, would emerge as logical necessities rather than empirical accidents. If such a theory exists, then the question of fine-tuning dissolves entirely, for there would be nothing to tune. The universe would simply be the only way a universe could be. Albert Einstein spent the final 2 decades of his life in pursuit of precisely this kind of unification, working quietly at the Institute for Advanced Study in Princeton from 1933 until his death in 1955. Having already unified space and time into space-time, and having revealed gravity to be the curvature of that spacetime. Einstein sought to incorporate electromagnetism into the same geometric framework. He believed, with a conviction that never wavered, despite repeated failures, that nature at its foundation must be simple and beautiful, that the patchwork of forces and constants we observe must arise from a single underlying principle. He worked largely alone during those years, isolated from the mainstream of physics, which had moved on to quantum mechanics and the statistical descriptions he found philosophically unsatisfying. His unified field theory was never completed. Paper after paper emerged from his small office, each attempting a new mathematical approach, each ultimately falling short of the goal. Yet Einstein never considered this work a failure in any final sense. He understood that he might be attempting something beyond the reach of his generation, planting seeds that others would cultivate in their own time. The universe, he seemed to feel, owed us no guarantee that its deepest secrets would yield to any particular century's efforts. In the decades following Einstein's death, the quest for unification continued along several distinct paths. One of the most prominent began, curiously enough, not with gravity at all, but with the strong nuclear force that binds quarks together inside protons and neutrons. In 1968, a young Italian physicist named Gabriele Veneziano was studying the mathematical patterns in particle collision data when he noticed something remarkable. The scattering amplitudes he was calculating seemed to match a formula that had been written down 2 centuries earlier by the mathematician Leonhard Euler, a formula describing a particular kind of mathematical function with unusual properties. Veneziano's dual resonance model, as it came to be called, was not initially understood as a theory of strings at all. That interpretation emerged gradually, as other physicists examined the mathematics and realized that the formulas Veneziano had written down could be understood as describing the vibrations of tiny one-dimensional objects, strings, rather than point particles. When a string vibrates in different modes, like a guitar string producing different notes, it would manifest as different particles with different masses and properties. What had seemed like arbitrary diversity, the zoo of elementary particles with their various characteristics, might arise from a single kind of object vibrating in various ways. String theory, as this approach eventually became known, offered a tantalizing possibility for explaining the constants of nature. If particles are vibration modes of strings, and if the properties of those vibrations are determined by the geometry of the extra dimensions in which the strings move, then perhaps the constants we measure in our laboratories are not inputs to the theory, but outputs. They would be what they are because of the shape of the universe at scales far too small for us to directly observe, a shape that might itself be uniquely determined by mathematical consistency. This was the dream, at any rate. The reality proved considerably more complicated. String theory turned out to possess not one solution, but an enormous number of possible solutions, each corresponding to a different way. The extra dimensions might be curled up upon themselves, each yielding a different set of physical constants. The number of these possibilities is often estimated as 10 to the 500th power, a number so large that it exceeds the number of atoms in the observable universe by such a margin that comparison becomes meaningless. This vast landscape of solutions, far from explaining why the constants have the values they do, seemed to many physicists to simply relocate the mystery without resolving it. Meanwhile, other researchers pursued a different path to quantum gravity, one that did not require the extra dimensions and supersymmetry of string theory. Loop quantum gravity, developed primarily by Carlo Rovelli and Lee Smolin during the 1980s and 1990s, attempted to quantize space-time directly, applying the principles of quantum mechanics to the fabric of the universe itself. In this approach, space is not continuous, but woven from discrete loops of gravitational field, tangled together in intricate patterns that give rise to the smooth space-time we perceive at larger scales. Loop quantum gravity offers its own perspective on the question of fundamental constants. If space and time themselves are discrete, built from smallest possible units, then perhaps the values of the constants are determined by the combinatorics of how these fundamental pieces fit together. The theory remains incomplete, and whether it will ultimately explain the constants or simply take them as given is not yet clear. But it represents a genuinely different approach to the same ancient question, a reminder that the path to deeper laws may run through unexpected territories. Some physicists have proposed that the constants of nature are not fixed for all eternity, but change over cosmic time, perhaps resetting themselves with each cycle of a universe that expands, contracts, and rebounds. In 2002, Paul Steinhardt and Neil Turok developed a cyclic model of the universe in which our Big Bang was not a singular beginning, but merely the latest in an endless series of collisions between vast membrane-like structures called brains. In each cycle, the constants of nature might take on different values, determined by the precise manner of the collision and the subsequent evolution. Our universe, in this picture, is simply one frame in an infinite cosmic movie. Its constants no more permanent than the patterns in a kaleidoscope. Such cyclic models do not eliminate the question of fine-tuning so much as they transform it. If the constants can vary from cycle to cycle, then we might still ask why this particular cycle happens to have constants suitable for complexity and life. The answer might be anthropic after all, or it might involve some selection mechanism we do not yet understand, some cosmic Darwinism that favors certain configurations over others. The cyclic view reminds us that even our deepest assumptions about the permanence of physical law might be provincial, limited by our experience of a single epoch in a much longer cosmic story. Not all physicists are convinced that the search for deeper laws is on the right track, or that our intuitions about what those laws should look like are reliable guides. The physicist Sabine Hossenfelder has written extensively about the dangers of what she calls naturalness arguments, the assumption that fundamental constants should take values that seem natural or elegant to human mathematicians. She points out that physics has no guarantee of being simple or beautiful by our standards, that the universe is under no obligation to be comprehensible to beings who evolved to find food and avoid predators on the African savanna. Our sense of what is natural, she suggests, may tell us more about ourselves than about the cosmos. This critique does not necessarily mean that deeper laws do not exist, only that we should be careful about assuming we know what form they will take. The history of physics is littered with examples of principles that seemed natural and obvious until they were overturned by experiment, and with phenomena that seemed arbitrary and ugly until a deeper theory revealed their hidden elegance. Humility about our current understanding does not require abandoning the search for greater understanding. Some physicists have suggested that information itself might be the most fundamental category, more basic than matter or energy or even space-time. John Wheeler, the physicist who coined the terms black hole and wormhole, proposed in 1989 a hypothesis he called it from bit. In this view, every particle, every field, every force arises ultimately from information, from the answers to yes or no questions about the state of the universe. Physical reality, in Wheeler's aphorism, emerges from the act of asking questions and receiving answers. A participatory cosmos in which observation and existence are intimately entangled. Wheeler's vision remains more philosophical than mathematical, a suggestion of a direction rather than a detailed theory. But it has found echoes in more recent developments, particularly in the holographic principle first proposed by Gerard 't Hooft in 1993 and elaborated by Leonard Susskind and others in subsequent years. The holographic principle suggests that all the information about a three-dimensional region of space can be encoded on its two-dimensional boundary, like a hologram that contains depth in a flat surface. If this is true, then perhaps space-time itself is an emergent phenomenon, a projection from some more fundamental level of description where information is primary. What these diverse approaches share is the conviction that the constants of nature, rather than being arbitrary parameters, are in some sense necessary. Nobel laureate David Gross, who shared the 2004 prize for his work on the strong force, has expressed confidence that future generations will derive the constants from first principles, that what seems contingent today will appear inevitable tomorrow. This is a statement of faith in the comprehensibility of nature, a belief that the universe makes sense all the way down. Whether this faith is justified remains an open question, perhaps the deepest question in physics. It is possible that the constants will be derived, that some future theory will explain why the fine structure constant is 1/137 and not some other value, why the ratio of proton mass to electron mass is 1836 and not 1900, why gravity is precisely as weak as it is relative to the other forces. In that case, fine-tuning would dissolve as a problem, revealed as an illusion born of incomplete understanding. But it is also possible that the constants are truly contingent, that they could have been otherwise, and that no theory will ever explain why they are as they are. The universe may simply be one possibility among many, selected by chance, or by anthropic necessity, or by some principle we have not yet imagined. The mystery may deepen rather than resolve as we probe further into the foundations of physics, revealing new contingencies we had not suspected, new parameters that seem arbitrary, new coincidences that demand explanation. For now, we find ourselves in the middle of this story, not at its end. The search for deeper laws continues in universities and institutes around the world, in equations scrawled on blackboards and simulations running on computers, in quiet conversations over coffee, and in papers posted to electronic archives at all hours of the night. Physicists of every persuasion continue to chip away at the foundations of reality, motivated by the same conviction that animated Einstein in his small Princeton office, the sense that nature must be comprehensible, that truth is worth pursuing even when the pursuit extends beyond a single lifetime. And so we hold these possibilities gently, the various paths that might lead to understanding, the alternative theories and competing approaches, without insisting that any one of them is correct, without demanding that the universe settle the question on our schedule. The fine-tuning of the constants remains, for now, a mystery, a feature of reality that invites contemplation rather than conclusions. Perhaps that is enough for tonight, to have surveyed the landscape of ideas, to have glimpsed the various directions in which understanding might grow, and to rest now in the knowledge that the search continues, slowly and carefully, in the manner of all genuine inquiry. And so we arrive at something quieter now, something that draws the vastness we have been contemplating back toward you, back toward this moment, this breath, this gentle descent into sleep. We have spoken of forces and constants, of carbon nuclei resonating at precisely the right energy, of gravity balanced against expansion across billions of years. But all of these cosmic arrangements, all of these improbable calibrations, lead eventually to something very simple and very near, which is you, lying here, breathing slowly, made entirely of ancient starlight. The astronomer Carl Sagan, in his 1980 television series Cosmos, offered a phrase that has since become a kind of gentle mantra for those who contemplate our place in the universe. "We are made of star stuff," he said. And by this, he meant something quite literal, something that bears repeating now as you settle more deeply into rest. The atoms that compose your body, the calcium in your bones, the oxygen filling your lungs, the carbon forming the intricate molecules of your cells, none of these elements existed at the beginning. The early universe contained only hydrogen and helium in any significant quantity, the simplest atoms, born in the first few minutes after everything began. Every other element, every heavier atom that now participates in the complex chemistry of life, had to be forged later, in the nuclear furnaces of stars. Consider, if you will, something as ordinary as the iron in your blood. At this moment, hemoglobin molecules are carrying oxygen through your bloodstream, and at the center of each hemoglobin molecule sits an atom of iron. This iron was not always here on Earth. It was not always anywhere, in fact, because iron atoms are created only under the most extreme conditions the universe can produce. The iron in your blood was synthesized approximately 4.6 billion years ago, in the final moments of a massive star's existence. That star, somewhere in this region of the Milky Way, had burned through its nuclear fuel over millions of years, fusing lighter elements into heavier ones in its core. When it reached iron, it could go no further, because iron fusion absorbs energy rather than releasing it. The core collapsed. The star exploded as a supernova, scattering newly forged elements across light years of space. And some of that scattered iron eventually found its way into the cloud of gas and dust that would become our solar system, then into the forming Earth, then into the oceans where early life emerged, and finally, through an unbroken chain of living things, into you. Every atom of iron in your blood has this same history. Every atom has traveled through at least one dying star. You carry within you the remnants of ancient stellar explosions, and you have carried them all your life without perhaps giving it much thought. This is not poetry, though it sounds like poetry. It is simply what happened, verified through decades of spectroscopic analysis and nuclear physics. You are, quite literally, made of the same material as stars. And it is not only iron. The oxygen you are breathing right now, the oxygen that fills this room and sustains your quiet respiration, was also forged in stellar cores. Some of those oxygen atoms have histories that stretch back 8 or 10 billion years, to stars that lived and died long before our sun was born. When you inhale, you draw in atoms that were once part of other stars, other solar systems, possibly other worlds. The air you breathe is ancient beyond comprehension, recycled through countless cosmic processes, and now participating, briefly, in the chemistry of your consciousness. Every breath contains approximately 10 sextillion molecules, which is a 1 followed by 22 zeros. Given the mixing of Earth's atmosphere over billions of years, it is statistically certain that every breath you take contains atoms that were once breathed by every human being who has ever lived. But beyond that, those atoms were once inside stars, inside nebulae, inside the dust that drifts between galaxies. The boundaries we imagine between ourselves and the universe are, from a physical perspective, entirely illusory. You are not separate from the cosmos. You are a temporary arrangement of cosmic material, a pattern that matter has assumed for a brief time before dispersing again into the larger whole. The astronomer Michel Thaler has spoken about this in terms that seem fitting for this late hour. She has observed that we are the universe experiencing itself. And this is not a mystical statement, though it carries a certain wonder. What she means is that the matter and energy that make up your body are the same matter and energy that make up everything else. There is no special substance called life that was imported from somewhere outside the physical world. You are made of the same protons, neutrons, and electrons as the most distant galaxies. The difference is that here, in this particular arrangement, that matter has become organized in such a way that it can think, can wonder, can lie awake at night, contemplating its own origins before finally, gently, surrendering to sleep. Some astronauts have reported a profound shift in perspective when viewing Earth from space, a phenomenon that the author Frank White named the overview effect in 1987. When you see the Earth from orbit, or from the surface of the Moon, you see it as a single, fragile, borderless sphere floating in an immense darkness. The divisions that seem so important from the surface, the lines on maps, the distinctions between nations and peoples, become invisible. What remains is simply Earth, a pale blue sphere wrapped in a thin, luminous atmosphere, suspended in the void. Astronauts who have experienced this view often describe a feeling of profound interconnection, a sense that all life on Earth is part of a single system, and that this system is itself part of something much larger. You do not need to travel to space to understand this intellectually, though the emotional impact of seeing it with your own eyes is apparently quite powerful. You can simply lie here, breathing quietly, and recognize that the same physical laws operating in the most distant reaches of the universe are operating in your body right now. The gravity that holds galaxies together is the same gravity that keeps you gently pressed against your bed. The electromagnetic force that governs the behavior of light traveling across billions of light years is the same force holding your atoms together, allowing your neurons to fire, enabling you to hear these words and understand them. In December of 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky near the constellation Ursa Major. The patch was so small that it appeared blank to ground-based telescopes, covering an area of sky roughly the size of a grain of sand held at arm's length. They kept the telescope pointed at this tiny region for 10 consecutive days, gathering every photon of light that arrived from that direction. When the resulting image was processed, it revealed something astonishing. That apparently empty speck of sky contained more than 3,000 galaxies, each one a vast island of hundreds of billions of stars, each one unimaginably distant, each one home to its own planets, its own chemistry, its own possibilities. The Hubble Deep Field, as this image came to be called, demonstrated that the universe is populated with galaxies in every direction, as far as our instruments can see. Later observations have extended this finding. The observable universe, meaning the portion of the universe from which light has had time to reach us, contains approximately 200 billion galaxies. Some estimates place the number higher, perhaps 2 trillion when accounting for smaller, fainter galaxies beyond our current detection limits. Each galaxy contains, on average, 100 billion stars. This means the total number of stars in the observable universe is approximately 10 to the 24th power, a 1 followed by 24 zeros. For each grain of sand on every beach on Earth, there are roughly 10,000 stars in the observable universe. And yet, here you are, a collection of atoms that has somehow become aware of all this, contemplating the vastness from within it. The physicist Freeman Dyson, reflecting on the improbable conditions that allow life to exist, once offered a gentle conclusion. The universe in some sense knew we were coming, he wrote. This is not a claim about cosmic intention in any supernatural sense. Dyson was careful about such matters. What he meant, rather, is that the laws of physics seem remarkably, almost suspiciously conducive to the emergence of complexity, of structure, of life, of minds capable of looking back at the universe and asking how it all came to be. Whether this reflects something deep about the nature of reality, or whether we simply happen to find ourselves in a universe with these particular properties, because we could not exist in any other kind, remains an open question, but the observation itself is secure. The universe, as it happens to be, has produced you. You are part of this improbable, precious cosmic story. Consciousness has arisen from stardust, has looked out at the stars that made it possible, has wondered at its own existence for a little while, and now, here in this quiet moment, is preparing to rest. The same atoms that burned in stellar cores billions of years ago are now arranged in such a way that they can feel drowsy, can sense the comfort of a pillow, can hear a voice speaking slowly in the darkness. The stars are still there, of course, even if you cannot see them through your ceiling, even if clouds obscure the sky. They are burning steadily, fusing hydrogen into helium, and in some cases helium into carbon, carbon into oxygen, oxygen into heavier elements still. Some of them will one day scatter their contents across space, contributing material for future planets, future life, future consciousnesses that will lie awake, wondering about their origins before finally, gently, falling asleep. You are beneath those stars now, made of their substance, breathing their ancient light in the form of atoms that have traveled so far to reach you. There is nothing you need to do with this information, except perhaps let it settle over you like a blanket, another layer of warmth as you drift towards sleep. You are not small, though you are brief. You are not insignificant, though you are temporary. You are the universe, experiencing itself, resting now, returning for a few hours to the quiet darkness from which everything emerged, before waking again to another day under the same ancient sky. The iron in your blood is 4.6 billion years old. Your breath contains the remnants of countless stars. You are, in the most literal sense, made of star stuff, and the star stuff is now tired, and the star stuff is now safe, and the star stuff is now allowed to rest, here at the end of this long, gentle contemplation, beneath the same cosmos that made you possible.